So we did a first initial trial run that would give us a better understanding of how the fuel reacted and experimented on campus, as it's never been done before on campus. And so we mixed it in the fuel bowl behind the prop lab and then cast it, and we focused on note cards with this initial mix with a smaller to understand how it was going. And then once it was able to be placed in the fire cabinet and go back, we initially found that it did not cure to a solid state. We were able to demonstrate and find this out because of the tacky texture of it when we were trying to demold it from the note card, as well as the fact that it did not hold its shape within the note card itself. So taking it out of the note card, it did not reform to that square shape that is shown. We then went back and made changes to our composition, which was shown in slide 31, where we increased the amount of curative that was used. And then we also increased the vacuum and shaker table time that it was on, so that we would have a more homogeneous mixture and so that it would be able to mix better and have less air pockets within the actual fuel itself upon casting. As you can see in the image, there is us performing the mix with the vacuum and the shaker table. We then cast that fuel into a note card as well as a smaller grain to test and see if this new composition would be able to cure to a final state, and we were able to do so. And we noticed that after being placed in the fire cabinet and allowing for the accommodated time, it did cure to a fully solid state, as it was able to retain and hold its shape even after being moved around. So it's able to retain that final square note card shape, and then we had a successful test from this. Next, we'll be going into our igniter.
Thank you. So over igniter, as you can see in the system, it's going to be located at the top of the fuel grain nearest to the injector. A quick overview of it, it's similar to the fuel grain. It's a base grain with the outer diameter being the exact same as the inner diameter of the fuel, and the inner diameter of the igniter being 1.25 inches, hopefully to get a 17-second burn time. Now, to prove all of this, because we've never used Symbo as a grain propellant, we've only used it in pellets, we did some igniter testing. The goals for this were to first verify that we were hitting that 17-second burn time, and then as well as we wanted to verify that the impingement of our exhaust for our igniter wasn't clogging our injector. So essentially how we went about this is we did our mixing on campus, how we usually do, made the igniters. From there, we connected it to test cell 1, set up the igniter, set the e-match, started recording, and then finally tested to validate that we are hitting our goals, and then finally checked the injector. This is what a test looked like. So as you can see, the picture on the right is our igniter, our injector, and that is our aluminum one, where we can see obvious damage by the exhaust. However, we were planning on making a steel injector faceplate, so we were not concerned about heat affecting or damaging the structural integrity of the faceplate. However, in this picture, you can tell that there is no clogging of the injector ports, which is great. It means that we satisfied that test. Then we wanted to move into our igniter solids testing, where we wanted to make sure that our igniter alone could create regression rate from our fuel grain. This was to prove that even without LOX, even without any oxidizer, we could still be getting fuel in our exhaust. And then finally, we also wanted to make sure that due to the fact that we were designing this to friction fit into our fuel grain, we wanted it to not eject down because we don't want to hurt any of the other parts of the engine. Same exact process. You mix your fuel grain and your igniter on campus. You adhere them to each other, or you friction fit them. You put them in test cell 1. You set up all your measurement systems. For us, it was just a camera. And then we measure our fuel grain with calipers after it's cooled down. And here's the test of that. And then finally, after that, we measured the fuel grains, and we could tell that there was 0.02 inches difference in our diameter, our inner diameter, which means that we did get regression greater than 0, which is great, which means that we satisfied the requirement that the igniter could actually regress the fuel grain and get fuel into our exhaust. Next, we will be talking about the engine case and lining.
And an overview of the engine case with everything start from the outside, we're looking at a 6061 T6 aluminum engine case, followed by a pre-combustion chamber that is made up of danger glaze. This is a thermal insulator, so that when combustion is taking place inside of this engine case, it can act as a thermal barrier, so that way we don't anneal the engine case. This also acts alongside the engine liner, which is a partially cured phenolic liner. So this is essentially like a really hard cardboard that's very thermally insulatory. And so following that, we have our casting tube. This slides into the engine liner, and this is made of craft paper and glassine. Craft paper is essentially like wax paper. It allows for that easy sliding in of the casting tube, and the glassine is essentially just paper that's been pulped from hardwood trees like birch and aspen. It's really just stronger paper. Following that, we have another post-combustion chamber, which is made up of danger glaze, just another thermal barrier for the combustion that's taking place inside of the engine case. Following that, we have brass bolts, which are in a 6-degree offset pattern from the nozzle, so that just holds everything in together. These are brass for a reason I'll get into in the next slide. Following that, we have our fuel grain, which Winona was just talking about. We have our igniter, which Finn was just talking about, and we have 6/4" 20 steel bolts, which are grade 5. And this was done so that we do not allow the injector to be broken off during testing. And the reason we want to do that is because we care about the engine case not turning into a balloon. But to give you guys a general overview of the size of the engine case, we have a 4.5-inch outer diameter and a 3.5-inch inner diameter. And our engine liner is sized by a third-party company. We just get it shipped in by a company. And they size it so that we're able to friction fit the liner into the inner diameter of the engine case. And they also make the casting tube, which we cure the fuel in. So we're able to then slide the fuel grain into the engine case. And the reason we're doing friction fit rather than bonding everything to the inside of the engine case is so that we can use this engine case for multiple testing if we would like to hot fire more than once in one day, or just continue to reuse this engine case. But in order to get to that point, we have to go through the crucial test, which is a hydrostatic test. And so the reason we do this is because we want to make sure that our analysis is correct in where our nozzle will be the first component of the engine to be ejected out of the engine itself. And so that's done using the shearing of the brass bolts that I was just talking about. And so in order to do that, we plug both ends of the engine case, we fill it up with water, and then we use a hydrostatic pump to fill the engine case with more water up until the bolts burst at a certain pressure. And so this is a video that you can see over on the right side of the screen. The engine case is filled up with water at the moment, and you can see that the brass bolts do shear. And this occurred at a chamber pressure of 750 psi, which is 2 times our operating chamber pressure, which is 375 psi. So this gave us the confidence to move forward in our test. This gave us the confidence to move forward in our tests, knowing that our case wouldn't turn into a balloon if we were to overpressurize during a hot fire. We instead safe. Sorry. Did you guys hear all that? Okay. Next up, Lisa will talk about the nozzle.
Thank you, Noah. You can see the nozzle here in the aft end of the engine, and this is a picture of the completed assembly of the nozzle with the nozzle insert as the brown black part in the center and the steel converter. The nozzle is comprised of those 2 parts, and it integrates with itself. The insert seats within the converter, and I'll discuss why that's important. This is, again, the picture of the actual assembly together, and it integrates together with the case, as Noah said, with the 6/4" 20 brass bolts, so that is the mode of failure, and as well as 2 O-rings. Now, the dimensions of the nozzle are seen here with the CAD cross-section on the left and the model on the right. I machined the nozzle converter out of this one seen up here is made out of low carbon steel which was made on the lathe, and it seats the nozzle insert inside using our high temperature RTV silicone. And this is important because the converter will increase the diameter of the nozzle insert, which means it will fit into our case while maintaining the same converging and diverging half angles, as well as the throat diameter of the nozzle. The converter will increase the exit diameter of the nozzle assembly itself so that we can optimize our flow with regard to our analysis. And see here, this is the nozzle insert that we've purchased that fits, it's up at the front, and those work together to optimize the flow at the end of the engine. So now that we have all of the engine sub-assemblies together, then we'll discuss the ground hardware.
Thank you. So essentially, the engine's built. How do we test it? We get it on our test cell. As you can see, the ground hardware is an engine stand and our thrust plate. What that looks like, big picture for our test cell. This is a CAD rendering of our test cell 3, where you can see our engine, the thrust structure that we bolt our thrust plate onto, then our feed system, which connects to our tanks, our doer that we buy from Lindy, and then finally our DAC cabinet that we use to measure data. Now here's the full engine assembly. As you can see, all the sub-assembly pieces come together. It rests on the thrust plate and then finally on the engine case. And then here's a picture of it actually integrated. As we have spoken before, we did not get to do a full engine test. However, we did be able to build all of it, which is pretty cool. Next, we will be talking about future work.
Thank you, Finn. As Finn just said, we'll be talking about future work. Unfortunately, due to time constraints in this semester, we will not be able to perform all the tests that we would have liked on this engine. Therefore, moving forward, we'll be passing this project down to the Rocket Development Lab, and specifically Project Perseus, who will continue the testing for us. The first test that we would like to have performed is a flamethrower test. Now, the goal of the flamethrower test is to ensure that the engine produces flames while the igniter is intact. This test will happen down at test cell 3 and follow all the standard operating procedures for an engine test. Essentially, this means there'll be a pre-test setup. From there, we will go into checking our valves, our system checks, our leak checks. Once this is all complete, we will then fill the system with our locks and begin the test. We will use cameras to visually see if the engine is producing flames. Taking a more zoomed in look at this, here's an image of our engine attached to test cell 3. The hardware we will be using is the thrust plate, the engine assembly, and the nozzle converter. Now, as Issa just talked about, the nozzle subassembly is comprised of mostly two components, those components being the converter as well as the insert. Now, for the purposes of the flamethrower test, we do not want to risk overpressurizing our chamber pressure. Therefore, we will not be using the nozzle insert. We will only be using the nozzle converter. This converter also will help during this test to keep the engine liner and the fuel grain from flying out during the duration of the test. Now, because that nozzle insert is not actually in the nozzle itself, the engine will not be performing at its max thrust. However, a significant amount of thrust is still expected from this test. And the last piece of hardware we'll be using, again, is those cameras, which will be set up at multiple locations around the engine to visually verify if flames have been produced. Once a successful flamethrower test has been achieved, the test team will then move on from the flamethrower test and into a hot fire test, which Finn will now discuss.
Yeah, so flamethrower, we get good ignition, sweet, great. Now we want to finish the project and actually say that we could hit that thrust requirement. So essentially what that is the goal is to hit that 250 pounds thrust for at least 1.5 seconds with a 10% deviation. That is normal operating procedures, same thing that Bree went through. However, we are using the nozzle insert in the nozzle converter to hopefully optimize our thrust to hit that. Now, what that means hardware-wise, again, the exact same hardware. However, now we're focused more on our load cell data. We're not focused as much on cameras, even though flames are really cool, and we'd love to see that. But really, thrust is most important, so we're focused on getting that load cell data to validate that we are hitting that 250 pounds thrust.
Now, we're going to go over our requirements again. we have met the first requirement due to the design of our engine. The last requirements will be completed in future work. We've proven that we have the capability of measuring if we meet the requirements, and we're looking for the results from Perseus to do that. Our total cost of the project was just under $2,000. Over half of that cost came from the liquid subsection. We had contributions from the College of Engineering and the University Research Institute totaling $3,000, which leaves us with a surplus of $1,100. We'd like to thank Professor Garrick, Dr. Adams, Loki Research, and Ray Melton from NASA. Thank you, and are there any questions?
I missed the first portions of your presentation, but I was looking at the bolt pattern for the assembly motor. I noticed you went with a radial pattern as opposed to more traditional axial pattern on this test article. Was there a driving factor for that design consideration?
So to repeat the question for the people on Zoom, is there a driving factor for having a radial bolt pattern rather than having an axial bolt pattern for the engine case? Traditionally, that's what's been used on campus, and so I've decided to follow tradition because this is new and we wanted it to be safe. And I think that was just the most straightforward way to go about it.
Typically, the reason I put into an axial configuration so the bolts are in tension as opposed to shear, so you just not want to keep that in mind.
So in your, I think in the ground hardware diagram, you had a support for the engine, but then in your actual test setup, it wasn't there. I just wondering what the reason was for that.
Yes.
Yeah, I lost it.
What we did find out though is that with the way that the injector is mounted to that thrust plate, we have these 3 bolts that bolt the back of the injector to that thrust plate, and then we have those 6 bolts that wrap around the injector to bolt the case on. We saw it was actually pretty rigid without having to need that structure. Of course, in hot fire conditions, we probably might see some vibrations and some other things. We might see some, wobbling. So that's what that most is supposed to do, is help with hot fire conditions. Miles?
So during your cold flow testing, you saw some issues around the oil out through your LOX line, both during chill and during actual sequences. You also, during your ignition testing, you saw your faceplate heating up a lot, and that ignition is going to happen after chill, but before liquid oxygen enters the chamber. Do you guys have any considerations or plans put around keeping that faceplate cold while your igniter is running, so you don't have that oil off and that overpress inside your injector?
So there was a fever dream of mine, which is that you run another line through that has a liquid LN2. So you are pushing a liquid nitrogen through during the ignition, and then after you then switch and you move to LOX. So that's something where we can keep it cold without pouring LOX into our chamber, increasing our OF ratio. That's something that maybe something Perseus can pursue. The other option is we decrease our baffle on our injector face. Maybe you can design an engine that has a higher mass flow rate, and that's the other option we were looking at. There also is discussions of just chilling for a really long time and letting that LOX evaporate. However, when you do have that igniter go off, you're right, your temperature is going to heat up that injector face.
Where's the thermocouple on the injector?
The thermocouple on the injector it's actually not it's upstream of the injector at the fitting stack there. Let's see if there's, it's a little bit past the actual injector itself. It's probably about 4 or 5 inches upstream, if I'm not mistaken.
So given that this is kind of the first time you're doing hybrid, right? Lots of experience with liquid, lots of experience with solid. What kind of safety considerations do you think you want to pass down to
is some history. 10 years ago, one of the first ever rocket projects on campus was a hybrid. And it did detonate down at test cell 1. And there is footage of that, but it's one of our first ever rockets that we tested on campus. And we actually learned a lot because we had some of the alumni that came down during our PDR's, our fall semester presentation. And they talked to us about some of their failure modes, and we took those into account. So we are working with passing on that knowledge from them to us, and now us to
One of the test pilots that was involved with the Virgin project wrote a great book. I can't remember the title of it, but one of the really big things Virgin struggled with and cost them a lot of time was there was a lot of internal team debate over the makeup and content of their hybrid rocket. And just, wondered if anybody had kind of looked at some of the history with Virgin's experience and get the maturity that they have.
Test gods.
Yes, that's the book.
Test gods.
Here you can see that's the actual test with that hybrid from 10 years ago.
Following up what he said, because I was on the safety review for that exact motor. That's all I'm gonna say.
Be careful with
Aluminum liquid oxygen.
Yeah, that's why we switched to 303 stainless steel for all of our
Yeah, just to touch on that as well, the biggest thing is startup and overpressing at startup. So that's why we wanted to do a bunch of pre-tests prior to make sure that we were validating that, like, even if we put the entire engine together and we did see overpress, we knew exactly what was occurring. And that's what allowed us to do cold flow. We knew how that looked. We knew how the igniter would operate. We knew how the fuel grain would operate. So that allows us to definitely create a significantly safer environment where we feel a lot more comfortable putting the nozzle converter on with the nozzle insert and going, yeah, let's make this a pressure vessel real quick.
Especially with Noah's design with the brass bolts on the nozzle section, but making grade 5 steel bolts on the forward section allows us to be confident that our photomailer isn't going to be detonation. Instead, we're shooting that nozzle down.
When you guys did your most recent cold flow, is that what you were talking about when you said engine reach steady state?
Yeah, can you go to that slide?
Have you guys like
Go
gone
to the
through?
zoomed in one. The zoomed in one, so the other direction. Left. Can you go to, yeah, keep going, there you are. You're talking about here.
Yeah. Have you guys gone through it, and do you know specifically why you didn't reach steady state and what you would do to change that?
Yeah, so the reason we didn't reach steady state is if we take a look at the temperature data, you see here that the injector only goes to minus 125 Fahrenheit, right? And because you have that temperature discrepancy between your oxidizer and your injector, your density is going to drop, your pressure is going to increase, and you can see that it is trending downwards, right? So hopefully those peaks that were supposed to be at that red line, instead we saw them higher. So in a condition where we're able to chill the injector, where we have a longer cold flow time, let's say we run a cold flow for more than just a few seconds, we can see this approach steady state, and hopefully we see level out around 500 psi.
Was this one continuous LOX main being open, or did you open it for a short time, close it, pressure decrease?
Yeah, in the video footage, you have two different tests.
So did you guys know that the hybrid 10 years ago was a failure due to the aluminum plate?
Yes, I remember you being here.
Yep.
Almost 4 months ago.
Yep,
Yeah.
I remember that too. So why'd you use an aluminum plate?
What was that?
Why'd you use an aluminum plate?
We did not. That aluminum plate was a plate I made to figure out how to easily manufacture the injector face.
Okay, so
that was
that was a
something that
mock-up.
was done during the assessor, and I gave it off to Finn to say, here, have this plate. I'm not hot firing it. You can go blow it up.
Okay, so that was a mock-up then, basically.
Here you can see that we have, this is steel, both the plates, the back plate and face plate are steel, and you see here that these are all steel plates. All of our hardware up here is steel. The only thing that's aluminum is our case.
Okay, so just a, I guess, presentation suggestion, make sure you plaster that on there, that the final one, like on the slideshow, is not going to be aluminum. Because if you have a range safety officer who sees that kind of thing, they might stop you right there, just because they've issued a warning. So that was cool. I was kind of like, why did you burn an aluminum plate when we talked about this? Okay, that's good to hear. Can you go to your hydrostatic test, please? So you guys said you sheared the bolts on this one?
Yes, you can see on the right side of the video, as it plays.
Yeah, I think I saw the nozzle move a little.
Yeah, you can see water shoot out.
Yes. And so you guys designed the failure point to be in those bolts, understand that. Was there any reason you guys pressurized the failure, or is it just more because you were curious?
That is the purpose of the hydrostatic test, is to see at what pressure you do fail at. And so we wanted to see the bolts fail at whatever pressure they were going to fail at. We calculated that they were going to fail at 750 psi, and that's what the test showed. And so that gave us confidence going into our following tests.
Okay. Yeah. Not to correct you because you're not entirely wrong, but you do proof tests as well, just to prove you can get up to pressure. You don't always do destructive hydrostatic tests. I was just curious why you had done a destructive one.
Yeah, we went to burst because we had the bolts, but we just wanted to verify that our burst is going to be our analysis one.
Yeah, and that's totally fair. Last but not least, and this is to kind of piggyback on Jacob's comment about your brass bolts. Do you guys know what temperature and what pressure those bolts will start to deform at?
Off the top of my head, no, but I can get it for you after this presentation.
Okay, that's not fully necessary. The reason I'm bringing it up is if the bolts are strong enough and you're confident in that, you want to make sure they're not going to bend, because they're going to become a pain to get out if that happens. Brass is notoriously soft, which, okay, you might be able to get them out, but you might damage your case getting them out.
Yeah.
So
Both Noah and Joey spent a great deal of time getting those sheared bolts out, all 6 of those holes.
Yep.
because we had
Sure
to
they did.
fix this case. Yeah,
That is true.
We
Yeah.
have looked at the change in your tensile strength of those bolts under thermal loads.
yeah, just bringing it up from the standpoint of when you're working with test articles, you want to make sure you don't accidentally engineer yourself into a hole. Because sure, you may do the test, but you may not be able to recover that test article.
Thank you. Was there another question?
Question from the energetics guys.
I was just curious if you guys, if you were to do like any future iterations to improve solid fuel, or did you have to cure your set now?
So we were currently working with the solid fuel that we have, due to the limited amount of time that we have working on this project and where we've gotten so far, we weren't probably going to make any iterations. Any iterations we were going to change would happen after the hot fire we see and depending on that regression rate that we see. But until we are able to conduct those like initial hot fire tests, we aren't able to make any changes to the composition yet because we currently don't know how it's going to perform under a hot fire. Thank you for your question. Any others?
Just a general comment, I guess. This is moving along very well. This is very good to see. Hybrids are tough, and they're known to be tough. So you guys did a good job getting as far as you did. Actually, I do have a question. Sorry, I forgot about this earlier. Can you go to your budget page? Was the reason for the discrepancy in funding because you guys didn't do your final test?
It was the consumables.
Got it. Okay.
And also currently ITAR and purchasing chemicals.
There were multiple things. Originally, our budget was for ERAU, which is significantly more expensive compared to locks. So when we made that design change, our budget decreased significantly, mostly because of that reason. But also purchasing of chemicals, ITARs were taken away, so we haven't been able to purchase those chemicals, which also reduces our budget. Originally, the price was using a lot more of the funds that we had than this.
Yep. No, I understand. Just wanted to understand the delta.